All right, so welcome to tonight's lecture. As I said, we're going to be looking at vectors. Then under vectors, we'll discuss what a vector is, which I believe most of us know, and what a scalar is, which I know that most of us know what a scalar is. Yeah. Then we'll also look at addition of vectors using graphical methods, subtraction using graphical methods, and also multiplying the vectors by its scalar. Then apart from that, we'll also look at resolving vectors into components. Yeah, which is one of the, I think, which may just be one of the a bit challenging part to some individuals. Yeah, so vectors, this is a very short topic. It's not something that we're going to even take long to finish. Yeah, so I think we'll just spend less than 30 minutes and then we are done. Then immediately after that, I'll just sleep a bit just to rest, and then I'll begin making tutorial videos for the tutorial sheets. And I'll send them to your groups. All right, so let me quickly begin. So everyone is able to get me. Okay. All right, so as I said, we'll start first by defining what a vector is. So when you hear about the word vector, what comes into your mind? So a vector is just a quantity in physics, or yeah, let me say in physics, because we're learning physics, but it's just a quantity wherever you are. It's a quantity with a magnitude and direction. Though there are also what we call vectors in biology, which is another thing again. Okay, so in physics, a vector is just a quantity which has both direction and magnitude. Then we also have what is known as a scalar. A scalar is a quantity, just like the opposite, not really 100% opposite, but it's just almost 50% opposite of what a vector is. So a scalar is simply just a quantity which contains a magnitude but has no direction. So this is what I was just talking about. So some vector quantities are displacement, we have velocity, we have a force and momentum. These are vectors. That's the reason why when representing displacement or velocity or a force, in most cases, in most books where they take vectors into consideration very much, you discover that they put an arrow on top. Yes, if not an arrow, this arrow is put there to show direction. And then if they do not put this arrow, sometimes they just put a bar on top. If they say A and then there's a bar on top there, means that what they have written there is a vector. Okay. So scalars only has magnitude, and some scalar quantities are mass. We have time and temperature. Let's look at how you can add vectors. Yeah, so vectors in one dimension are simple. Addition and subtractions are all that is needed. Right, so if you have a vector, let's say for instance, I'll give an example. If you have a vector that is, I'll draw an XY plane. If you have a vector that is in just one dimension. What we mean when you say a vector is one dimension, meaning it's either only in the Y or in the X. So for instance, if you have vectors in the X, let's say for instance, you have vector, okay, I'll draw it a bit on top of the x-axis, just for you to see what I'm doing. So if you have a vector, let's say vector A, you also have vector B in the same direction. So adding these two vectors, you just say A plus B. And if A, for instance, the magnitude is 20 and B, the magnitude is 30, meaning the answer will just be 20 plus 30. As long as it's just in one dimension, you just do it directly. So if you have maybe vector A like that, or let's say vector C, then you also have maybe vector D, which is in this direction. So if you have such, means that what you're going to do is that we know that C is facing to the positive side of the x-axis, or it's going towards the positive side of the x-axis. If, for instance, we take this side, the right, as our positive, so normally, and in most cases, the right is always taken as positive, and then up is always taken as positive as well, down as negative. So in this case, if we take the right-hand side as positive, it means that we're going to say C will be positive, and then this, since D is going against, or rather, it's going away from what we have taken as positive, it means that we're going to consider that to be negative. Hence, we'd say negative D. So adding vectors in 2 dimensions is straightforward. Now let's say, for instance, if C is 20 maybe kilonewtons if it's a force, and then you also have D, which is maybe 80 newtons. Yeah, so you just have to say this is 20 rather, not 30. You have to say 30, and then you have negative 80. So when you add that, you are getting negative 60. So this is the vector, meaning the resultant force or the resultant vector will be facing away from what you have taken as our positive. Okay, so it's just as simple as drinking water. Then we'll also look at adding vectors which are not in 2 dimensions. We'll look at all that. So you do not need to be careful about the signs. I mean, you do need to be careful about the signs, as the figure. Let me show you. There's a figure here that you can. Yeah. So when you look at this, we have these 2 vectors, 8 kilometers and 6 kilometers. When you add these 2 vectors, the answer, which is the resultant, is simply just 14 kilometers. Yeah, so in this case, all the 2 vectors, this one and this one, are facing the same direction. So there's nothing like subtraction. Just add them direct, 8 plus 6, and the answer is 14. Okay. Then you also have these 2 vectors. You have this small vector here, which is shorter than this one. Or let me not use the word shorter than, it's small in magnitude compared to this other one. So rather, oh, sorry, you have this one, which is bigger than this one in terms of magnitude. So you have 8, and then 8 is facing towards the positive, so just write it as positive 8. Then you also have this 6, which is facing against the axis. It's facing this side. It's facing away from the positive x-axis. So we consider this to be a negative 6. So we say 8 and then negative 6 there. The answer is 2. So the answer is 2. Positive 2 kilometers is our resultant vector. So let's look at another part of vectors. So adding vectors using graphical methods. Okay, so if the motion is in 2 dimensions, the situation is somewhat more complicated. So if you have a situation where the vector is in 2 dimensions, that one is a bit complicated, not actually even complicated, it's simple. Let's see what you do. So if you have a vector, for instance, that is in 2 dimensions, so meaning you have a vector in the x and in the y, and then you are required to add the 2 vectors. You have, let's say, for instance, you have this vector, and then you also have that vector. So adding these 2 vectors will require you to use what we call Pythagoras theorem. So the Pythagoras theorem is the one that you're going to use to add these 2 vectors to find the resultant vector. So what you're just going to do, if let's say, for instance, okay, let me use these same numbers here. Yeah, so if let's say, for instance, this one is 10, it has a magnitude of 10. So we say to find the resultant vector dr, say this one is equal to the square root of, and then you take this distance, which is here, this is just 10. So say 10 squared Then you also have this other distance, which is D2, which is this one will be 1, 2, 3, 4. So this one is 4. So plus 4 squared. So the resultant vector will simply just be equal to, this will be 100, then plus 16 squared, rather 4 squared, this will give us 16. So when you add these two, you get 100 plus 16, which is just the square root of 116. So this is how you deal with vectors that are in 2 dimensions. So vectors in 2 dimensions, you use Pythagoras theorem. Yeah, so this is how simple it is. So now, what if you have maybe vectors which are like this? You have maybe a vector. Okay, that one we use components. I'll show you how to deal with it. I wanted to write something like, maybe you have a vector which one is going like this, you have another one, then you have another one like that. So there's a way you resolve those into components and then you add everything together. Right. So I wish I had put some examples at the end from your tutorial sheets. Anyway, I'll just put them in, rather I'll just solve them separately and then send them in the group so that you can find time on your own to solve them through. Right, okay. So addition of vectors using graphical methods, we're still on graphical methods. Right, so what you should know is that if you have the vector, the first vector v1, if you add it to v2, this one is just the same as v2 plus v1. So in other words, vectors can be, okay, vectors obey the commutative law. If you have done mathematics, laws in mathematics, when you change the arrangement, the answer that you get will still be the same, provided the signs are just the same. Okay, so what they mean is that if, for instance, the one that we started with, we used this one. We used this one and this one. So if you want, you can also use the other route, this one, then you go like that. You still find the same answer. Okay. So even if the vectors are not at straight angles, they can be added graphically by using the tail to tip method. So tail to tip method, this is the method that most of you are using in grade 12, where you say vector A, if for instance you have the vector A, which is maybe for instance, vector A is maybe 2, 3. Then you also have maybe vector B, which is 5, 6. Yeah, so if you have these two vectors, so this one, if you have these two vectors and then they ask you to find the vector AB. So the vector, if they tell you to say this one is the tip, then this one is the tail. Yeah, so what you just do is, to say vector AB will be found by the tail, meaning we say B minus, if these two vectors are position vectors, so meaning we say OB minus OA. So we always say the tail minus the tip. That's how it is. Or sometimes they say the head minus, okay, if you have this, okay, let me do this. If you have, this is the head and then this is the tail. So when finding a vector, if you have maybe, let me just draw them properly. You have two vectors. Yeah, so you have two vectors. If these are position vectors, you have the origin there, which is O. Then you have maybe you have this one. You have this vector OA. Then you also have OB. You have OA and then you also have OB. Then they ask you to find AB. So to find AB, you're just going to say AB will be equal to OA minus, or rather OB minus OA. So start with the head, and then so it's always head minus tail. Yeah. So we start with the head. So meaning this is going to be OB minus OA. That's how you do it. So it's just the same as saying you start first by going to B, then from B there, that's when you go to, I mean, that's when you, to find this, what is the magnitude of this vector, which is the resultant vector. So you start with going first using the root OB, and then you, for this one, you're going to move. Okay, let me start from this side. So that's the same as starting from O there. We're moving from the tail to the head. So start from OA there. So we go against the direction of OA. So if we're going against the direction of OA, which is this one, means that we're going to have a negative on OA. Then for OB, we'll just use its direction like that. So meaning this one remains positive. What I mean is that we know that OA is like this, but when moving from the tail to the head, we're going to first move against OA, because we know that OA is in this direction. So we'll move first against OA, which makes it a negative OA. Then from there, we'll move from O there, and then go to B there. So move from OA and then positive OB. That's why we always have AB being equal to OB and negative OA, because we are moving against OA, so I'll have a negative there. Then OB will still remain positive. Yeah, so that's how we mean if we say vectors that are not at right angles. That's how you add graphically vectors that are not at right angles. Yeah, so the previous vectors that we looked at, these ones, they were at right angles. I mean, this vector was, the two vectors were at right angles, meaning we had a 90 degrees at one point. But if you have two vectors which are not at right angles, this angle, let's say for instance, is just theta, then you don't have, this is not a 90 degrees angle, meaning they are not this is not a right angle in short. So you have this, and then for instance, if they are position vectors, they are coming from the same origin. Yeah, so position vectors are just vectors coming from the same origin. So you first have to move against OA and then go to OB to find the resultant vector, which is R. Okay. So it's just as simple as that. Yeah, so this is exactly what we are talking about. So when you look at these three vectors here, we have this vector v1, also have v2 there, also have v3. So adding these two vectors, you first have to combine them. You first have to combine them. You're going to have the resultant, which is here. So the first one that we have is v1 here, which is the one that I've just put there. Then we have v2, which is this one here. Then we have v3s, which is this one. So when you combine these three vectors, you come up with a resultant, which is just VR. Okay, so it's very simple. And then the parallelogram method may also be used. Here again, the vectors must be tail to tip. So it's just the same thing that we talked about. So the parallelogram rule is this one. If you have a vector, for instance, v1, this example that we've given, then you also have this other vector v2. So the correct way of saying, the correct way of finding the magnitude of, or rather the magnitude of the resultant vector for these two vectors, v1 and v2, you don't say, yeah, so the correct way of finding this would be this one here. It's tip to tail. So meaning you first have to move from this point to that point, and then from that point to that point. Yeah, that's how you add vectors. So you can't say, yeah, so you can't say this one, I mean, the resultant vector is this one, this side. No, not correct that way. This is what they are also trying to tell you here. Okay, so this is what they're trying to tell you here. You have vector 1 and vector 2. When added together, you get VRLN. Same applies to this part. You have this vector and this vector. When you add them, you are getting this resultant vector there. Yeah, so the incorrect part is this one. So take note of this part. This is where a lot of people make mistakes. When you have this vector and another vector like that, you don't say the resultant is this one. No, the resultant should always be there. All right, so subtraction and multiplication of vectors by a scalar. This one is straightforward. When you're subtracting two vectors, you just do the same things that we were doing. So any vector that has a negative, it means that it's going towards it's going against the position, or rather the direction that we've assumed to be positive. So if we have assumed that the direction, this direction is our positive. If we have V as a positive vector there, any negative vector, it means that any negative vector will point against, or it will point in this direction. Any negative vector will point against the normal direction that we have assumed to be positive. That's what we mean by having a negative vector. So any negative vector is in the opposite direction of the original direction that we've taken to be positive. Yeah. So if we say, let's say you have vector A, and then we say maybe find 2A. So 2A will simply just be 2 times this vector. So it will be this, another vector like that. So when you cut it in between, you discover that this distance there is equivalent to that distance. So when you add these two vectors, you get 2A. When you multiply these two vectors 2 times, you get 2A, which is I mean, in this case, this 2 is the one that we call the scalar. So we've multiplied a vector there, which is vector A, by a scalar. All right. So this is what I even actually started by explaining. This is the one that this is the part I started explaining the time I was talking about position vectors. If, for instance, you have two vectors coming from one, you have two vectors coming from one origin, then you've been taught to add these two vectors, v1 and v2. So the way you add these two vectors, you say the resultant will be this one, as we discussed. And then we have this v1, we can write a parallel vector to it, which can be written as also there. So adding these two vectors would be v1 plus, v2 plus v1. Yeah, so this is what it means, v2 plus v1. So if you have these two vectors coming from the same origin, this is how you do the addition. And then if you have, let's say, for instance, a vector which is maybe in the negative, let me just be circling here. We have this vector which is in the negative of the original direction when you take the positive x as positive. So if you have this vector which is in the other direction, we call it a negative vector. And then you also have this v2. So adding these two vectors is just the same as saying v2 and then negative v1, which is just the same as v2 minus v1. So these things are straightforward. Next time when we meet, that's when we'll at least go. That's when we discuss at least something that will be making sense. This is not physics. This is mathematics. So that's when we do physics, when you start projectile motions and kinematics, those things. When you start projectiles, those are the ones that we call physics. All right, so subtraction of vectors and multiplication of vector by a scalar. Yeah, so this is what I'm just talking about. Very simple. When you multiply a vector, you have this vector v. When you multiply it with a negative 2, it means that you're going to, this one will multiply itself 2 times, Then since there's a negative, it means that it will be in the other direction. So this is what has happened here. Okay. So let's look at how we can add vectors by components. Yeah, so if you have this, let me do this. If you have a vector, for instance, you have a vector coming from the origin there, then you've been taught to find, okay, if this is the resultant vector, and then they ask you to resolve this in two components. So you're going to find its y component and its x component like that. So if this is v, you're going to have vx, and then you also have v in the y. So vx will be just our vector in the x-axis, which is this one. Then we also have vy, which is the vector in the y-axis. So how do we resolve this now? This vector, how do we resolve it in two components? How do we resolve this vector in two components? So this one is straightforward. You don't even have to stress or overthink or take time. No, just use the simple SOHCAHTOA that we all know. SOHCAHTOA. So the one that, so we're going to take, we're going to assume that V has been given, V is known. So if V is known, and then we've been asked to find V in the X, and then if V is known and the angle is also known, theta. So we've been asked to find V in the X and V in the Y. So this one will be straightforward. So if we're finding the adjacent, when you look at Vx, Vx is adjacent to this angle theta. So if it is adjacent, it means that we're going to use, since we've been given the adjacent, we've also been given V there, which is the vector. We've been given V and the adjacent. So this V is simply just the hypotenuse. So we have the adjacent and the hypotenuse, meaning in the x-axis there, we're going to use k, which is from SOHCAHTOA, we're going to use k, which is just cos. So from there, we're going to say cos theta is equal to the adjacent over the hypotenuse. So what is our adjacent? So our adjacent, let me do this. So our adjacent in this case is simply just Vx, which is the vector in the x component. So our adjacent, let me write first, cos theta will be equal to the adjacent, which is the x component of the vector V, is just going to be Vx, and then the hypotenuse is the one that we assumed that we've been given. So we're going to write it as V there. So now to find Vx, we've been told to resolve V in two components. So now to find Vx, let me demarcate here. To find Vx, we are just going to cross multiply here. So Vx times 1, we get Vx. Then this will be equal to V times cos theta. So we say V cos theta. So this is how you find the x component of any vector. You've been told to resolve it into its components. And then we do the same even in y. So in the x-axis, in the y-axis here, in the y, to find the y component here, we can see that what we've been given in this case is the opposite to the angle, which is Vy. So we have the opposite to the angle, and then we've also been given the hypotenuse, which is just V. So the one that deals with the hypotenuse, which is h in short, let me write h. So the one that deals with hypotenuse and the opposite is sine. So sine is the one that we're going to use. So we're going to say sine theta is equal to the opposite over the hypotenuse. So in this case, what is our opposite? Our opposite is Vy. So I'll not write this side. I'll say sine theta is equal to the opposite will be Vy, and then everything divided by the hypotenuse. So the hypotenuse is the one that we have as our V. So I'm going to write V there, and then say divide by 1. So when we cross multiply everything there, we're going to have Vy is equal to V sine theta. So this is very important. It's very important, and you're going to use it almost on every topic, almost on all the topics that we're going to learn in physics. So you have to know these two formulas. In the x-axis, you use v cos theta, and the y-axis, you use v sine theta. So in other words, it's just the same as hypotenuse times theta, or the vector that we've been given. If, for instance, this v was 20 kilonewtons, if this v was 20 kilonewtons, and then they ask you to resolve this 20 kilonewtons into components, you just say in the x-axis, you say v in the x-axis will just be 20 cos 20 cos the theta that we've been given there. If it's 20, you write 20 then. So, and then in the y, you are going to say vy is equal to 20 sine theta. This is exactly how you do, or rather how you find the components of any vector. It's very simple. You don't have to even take time or to assist to think about how you're going to solve such. All right, so that is exactly what you are supposed to do. All right, so for instance, if you have this, so these are the things that I was talking about. These are the, yeah, and then the other thing, the most important thing that you need to know is how to find the angle. How do you find the angle given the components of the vectors? So finding the angle given the components of the vectors from SOHCAHTOA again. SOHCAHTOA. So from SOHCAHTOA, you've been given the adjacent, which is this one. You've also been given the opposite to the angle. So it's opposite to the angle. That's why I'm calling it the opposite. So you've been given the opposite and the adjacent, and you've been asked to find the angle which is there. So this one is straightforward. You just say, you just use tan. So we know that tan theta is given by the opposite over the adjacent, opposite over the adjacent. So in this case, what is our opposite and what is our adjacent? So the opposite is simply just Vy, and then the adjacent is Vx. So this is just the same as saying Vy over Vx. So this is exactly how you find the angle. They ask you to find direction. Every time they ask you to find direction in physics, they are asking you to find the angle. Every time you hear a question, find the direction of this vector or find the direction of this vehicle, it's the angle they're asking you to find. Yes. And then to find the resultant, or to go back, to get back to this vector, if you've been given the what is the components, it's straightforward. You use Pythagoras. How do you use Pythagoras? If you're finding the hypotenuse, you say the hypotenuse squared is equal to the opposite squared plus the adjacent squared. So the hypotenuse in this case is the v that we're finding. This one is equal to, the opposite is Vy. So we say Vy squared plus the adjacent, which is Vx. Yeah, so the formula now becomes V is equal to the square root of V. You can even interchange them, there's no problem, because addition is commutative. Vx squared and then Vy squared. So this is how we find the magnitude of a vector if you've been given the components. Right, so I'll send some of the recorded sessions, which I think I recorded some of them on, questions on the components of vectors. So you can find time to go through them. Okay, so these things are simple. Yeah, so next time we're going to meet, we'll look at, we'll start what's this, projectile motion. Yeah, so start projectile motion, also look at other things that are very important. All right, so if you have, for instance, this vector, if you have this vector, for instance, V, and then you've been taught to add V, you've been taught to add V1 and V2 to find this resultant vector. And then if these vectors are in space or they're in the X or Y plane, so we know we have V1 here, and then also we have V2 there. Then you've been taught to add these two vectors to find this resultant vector. Let me draw it separate. So we have this vector, which is v1. We also have this other vector, which is v2. So now we've been told to find this resultant vector. Yeah, we've been told to find this resultant vector vr. So this one is straightforward. You don't just use Pythagoras, because Pythagoras in this case will not work. Why? Because the angle that we have here is theta. This theta here is not a 90 degrees angle. So Pythagoras only applies when the angle here is a 90, or in at least in the triangle, if we have at least one, at least if you have a 90 degrees angle, that's when we can apply Pythagoras theorem. Otherwise, you don't apply it. So whenever you find such vectors, you first have to express them into their components, meaning you're going to find, let's say if I take vector 1, which is just v1. So I'm going to find the x component of v1, so which is just going to be v1x, and also the y component of v1, so v1y. Yeah, so this will be vy1. So after finding the x component of v1x and of v1 and the y components of v1, I'm also supposed to find the x and the y components of v2. So I have v2 there. So I'm also supposed to find v2 in the x and v2 in the y. And then from there, to find the resultant. Now, to find the resultant means that I'm going to add, I'm going to say vx, v1x, then plus v. Okay, this is what it's going to be. So to find v, I'm going to say the square root of, I'll add the x components, this one and that one, and then I'll square them. So I'll say v1x plus v2x, then squared, and then say plus v1y and v2y, then squared. It's just the same thing that I was explaining on the previous page. Okay. So we're going to end here for today. I'll send the slide in the group, and then I'll also send some videos which are going to use for practice on what we have learned tonight. All right, thank you very much. See you.